Ladies and gentlemen, please welcome Gordon Grant.
Good morning. I'm Gordon Grant. I'm the President-elect of the Earth and Planetary Surface Processes section, and it's my honor and privilege to welcome you all to the Future of Water session in today's Centennial Theater. To provide context for this, let us turn to a passage from the American novelist Tom Robbins. Water, the ace of elements. Water dives from the clouds without parachute wings or safety net. Water runs over the steepest precipice and blinks not a lash. Water is buried and rises again. Water walks on fire and fire gets the blisters. Always in motion, ever flowing, rhythmic, dynamic, ubiquitous, changing and working its changes, a mathematics turned wrong side out, a philosophy in reverse, the ongoing odyssey of water is virtually irresistible. Today, we are fortunate to have 5 forward-looking thinkers and scientists to help us understand where this odyssey of water is taking us into the future. And with that, I'd like to introduce our first speaker, Dr. Jay Famietti from the University of Saskatchewan.
Thanks very much, Gordon, and good morning, everyone. What I'm showing you this morning is a map that our research team has constructed using data from NASA's Gravity Recovery and Climate Experiment, or GRACE mission, which flew for 15 years between 2002 and 2017 before its successor, the GRACE follow-on, or GRACE-FO, mission was launched in 2018. The GRACE satellites are unusual in hydrology in that they really function more like a scale than, say, like a camera or a telescope. So they're effectively weighing monthly water mass changes for the large areas around the world. In this map, the blue colors represent places that gained water mass during the lifetime of the original GRACE mission, and the red colors represent places that lost water. So let's break it down and understand what we're looking at. First, we're seeing some of the biggest losers in terms of water are the ice melt due to climate change. So the Greenland and Antarctic ice sheets, the alpine glaciers in Alaska, Colombia, Peru, and Patagonia are melting away, driving up rates of sea level rise at a rate of about 3 millimeters per year. We see some other patterns that are related to climate change. The high and low latitude wet areas of the world are getting wetter, and the mid-latitude dry areas are getting drier. We see that the places where the extremes of flooding and drought are also getting stronger, which for this 15-year time period is very likely also related to climate change. And finally, we see that the depletion of several of the world's major aquifers, so we're seeing that they're being rapidly drained, and that's to provide water for irrigation for food production. If we take this map and we map it to a template of the world's 37 major aquifers that are recognized by the United Nations, we see that over half of them, about 20 of them, are past sustainability tipping points, meaning that we've been pumping up more groundwater than is being replenished every year. I want to return to the wet areas getting wetter and the dry areas getting drier for just a moment. The IPCC has been predicting this for some time. This is a slide from AR5, which was the 2013 report, and it shows the predictions for precipitation increases at high and low latitudes, so the wet areas getting wetter, and the decreases for the mid-latitudes, but it shows them for the end of the 21st century. And here's what we're seeing from GRACE, okay? So we're seeing that happening now. These are some of the time series so the upper one is the wet areas getting wet, and the lower one is the dry areas getting dry. So one of the implications for groundwater is that in the places that we use it the most, the red areas, those areas that are already dry, is that groundwater recharge will decrease as the dry areas get drier with less precipitation. So we may very likely see an acceleration of the rates of groundwater depletion. The overall picture then that we see is pretty complicated, and it shows us that the human fingerprint on the freshwater landscape through climate change, ice melting, changing extremes, and poor groundwater stewardship is a dominant force that's dramatically changing patterns of freshwater availability. But it also shows us that, and so these are the aquifers that I mentioned before, that we have a full-on global groundwater crisis. This is a piece that I wrote 5 years ago in 2014 with a few recommendations. We need to really recognize that we use more water than we have available. Many of the food producing regions of the world, I should have mentioned, because we're draining the aquifers to fuel irrigated agriculture, not only is our water security at risk, but our food security is at risk. And in many of those places where we grow food, we have chronic water scarcity. That's why we're in the red on that global GRACE map. We need to be thinking about hydrogeological exploration of the world's major aquifers the same way that we would if they were oil reservoirs. We don't do a great job in many parts of the world of measuring, monitoring, reporting both groundwater quantity and quality, understanding how much we have, how much we need, how these things are changing over time, and sharing those data across political boundaries. Conjunctive surface and groundwater use has to happen. Doing one and not the other is really a zero-sum game. And importantly, we need to start recognizing groundwater as a critical element of national and international water supplies. This type of agenda really requires a global call to action. I'll return to that point in my last slide. So how will we respond? Well, first and foremost, we really need to be keep doing the high quality research that we do. This is really our niche, right? This is our calling card. It's the single most important thing that I think we can contribute to society. But we need to communicate about it. And that communication could take many forms. And it could be for many reasons, but we need to do it. So it could be as simple as sending a one-paragraph explainer over to your local Congress member's office. It could be giving a talk on your research to a local water manager. There might be an opinion piece about a larger policy issue. But we really need, given the urgency, the rates of change that we're seeing in these maps, there's an urgency there. And so we need to communicate to help shorten that gap, the research to operations, right, the research to policy gap. We need to engage in more transdisciplinary research. Simply put, transdisciplinarity moves us beyond the interdisciplinarity that we're already comfortable with on campus, but we have to engage directly with production and use of knowledge outside of the academy, right? Outside of universities. So we have to be working with our water managers, our city climate change officers, our state and provincial agencies. These stakeholders need our help, and depending on where you are in the world, they often don't have the capacity to deal with the urgency that I'm talking about this morning. On that note, the stigma about applied research not being good enough for tenure and promotion is really no longer appropriate in a world in which the hydrology is changing so rapidly. I want to share a success story with you, which is an example of how transdisciplinary research and science communication came together to help pass California's Sustainable Groundwater Management Act of 2014. California was the last state in the U.S. to pass groundwater management legislation. It's now an established part of the narrative that university scientists working together with the Department of Water Resources, with the State Water Resources Control Board, and really extensively communicating through speaking, through writing, through government advising, played an essential role in getting SGMA, as it's called, on the ballot. SGMA passed in 2014. It's now being implemented across the state, and hopefully we'll have sustainable groundwater resources in California for decades and centuries to come. Finally, I want to close with another effort in communication that came out of the Chapman Conference on Groundwater Sustainability last October. This is an example of science-based communication by a community urging action on a global level by entities like the IPCC, like the UN and its SDGs, raising awareness at meetings like COP25, which is happening right now. It's a call to action on global groundwater sustainability, and we need to do this collectively because raising global awareness and attention is a heavy, heavy lift. So please take a look and consider signing the groundwater statement, which is found at this web address, and consider sharing it within your own networks. In closing, remember part of my title is how we respond, how will we respond? Please keep in mind that how we respond today will define who we are tomorrow. Thank you.
Ladies and gentlemen, Remco Eilenhout.
Yeah, good morning, ladies and gentlemen. My name is Remco Eilenhout from Wageningen University in the Netherlands. And I would like to make a plea for what I call opportunistic sensing as a novel way to inform hydrological science and applications. And what I mean with opportunistic sensing will become clear in a minute. What we're witnessing currently is a revolution when it comes to mobile cellular communications worldwide. This graph shows that already in 2013, the number of mobile devices used worldwide was surpassing the number of people living on this planet. And in order to be able to communicate between our mobile devices, we need infrastructure. And we're going to take a look at the potential of this infrastructure to complement dedicated sensor networks, such as weather radars in this case. Dedicated networks are very good in providing accurate and robust data, but they leave gaps globally as well as locally in metropolitan areas, for instance. And what we propose is to use the infrastructure that has been created to make mobile telecommunications possible to infer environmental parameters. So a first question that I'm going to tackle and positively answer is, can we use mobile cellular infrastructure to infer environmental parameters? Another question that one may ask is, can we use our smartphones themselves to infer environmental parameters? And finally, a question that we may ask is, what has citizen science installed for hydrologic science and applications? Now, if we take a look at the theory behind microwave attenuation, and the upper right-hand side shows you a graph of a power law relationship between attenuation, loss of signal, and rainfall rate. And what it clearly shows you is that for radio frequencies around 30 gigahertz, that exponent becomes nearly 1. That means that for radio frequencies around 30 gigahertz, attenuation is going to be proportional to rainfall rate. And by chance, I call that serendipity, microwave links used for mobile communications worldwide operate at frequencies around 30 gigahertz, which suggests that microwave links from cellular communication networks can be used as path average rain gauges. Let's see how this works for, in this case, one microwave link in the city center of the capital of the Netherlands, Amsterdam. On the upper left-hand side, you see time series of loss of power received signal level whenever it rains. On the lower left-hand side, we have used that power law relationship, which is actually nearly linear, to infer rainfall rates. And in the middle panel, on the lower side of the screen, you see rainfall accumulation. So this shows you that indeed a single microwave link can be used as a path average rain gauge. If you can do this for a single microwave link, you can do this for thousands of microwave links. And that is what we did in collaboration with one mobile network operator in the Netherlands. So on the left-hand side, you see rainfall fields inferred by means of opportunistic sensing alone, using microwave links from the cellular communication network of one provider. On the right-hand side, you see the best available rainfall product for the Netherlands, which is based on 2 weather radars, 35 automatic rain gauges, and 300 plus manual rain gauges. And what you can clearly see is that there is a striking correspondence between the two, which suggests that indeed microwave links from cellular communication networks can be employed to infer space-time rainfall fields at the ground. Now, obviously, the Netherlands is a country where dedicated sensing networks are already pretty dense. But there are large parts of the world where that is not the case, but still where people are using their mobile devices. And that means that also in those parts of the world, South America, Africa, parts of Asia, we could, in principle, infer rainfall rates from cellular infrastructure. And we've tried to do so for a number of countries in Africa. We've given a course in Burkina Faso a couple of years ago, together with German and French colleagues, informing meteorological and hydrological services about the potential of this technique. And we've also engaged through a collaboration with the GSM Association with mobile network operators locally, stimulating them to provide their data. And on the right-hand side of this screen, you see an example for the country of Nigeria, and in particular for the capital Lagos, which has over 20 million inhabitants and is actually the largest city on the African continent. And what you can clearly see, the lower moving picture shows you what can be obtained from about 8,500 microwave links covering the city of Lagos, and the upper graph shows you what can be obtained from a global precipitation measurement mission satellite product. What you can clearly see from this is that there is huge potential for using existing cellular infrastructure opportunistically to monitor our environment. Now, there are also other ways to sense our environment opportunistically, and one other way is to use temperatures of the batteries of our smartphones to infer inner city outside air temperatures at screen level. Now, clearly this cannot be done using each individual smartphone, but bringing together smartphone battery temperatures through a particular app that's been introduced by OpenSignal allows us to estimate inner city air temperatures for 8 major cities around the world, both in the Americas and in Europe. And the lower right-hand side shows you a graph where we demonstrate the potential of this technique for the city centre of London, comparing what can be obtained opportunistically with dedicated sensors at London City Airport, again showing the potential of opportunistic sensing, in this case of urban air temperatures, which are so relevant for studying the urban heat island, for instance. And finally, citizen science. More and more people these days are interested in monitoring the weather. They acquire meteorological stations which they install in their backyards or on the roof of their houses, and data from those sensors are available through the internet. And what we have been doing over the past years is trying to infer, in this case again, rainfall rates over the Netherlands from those stations installed by the public. Of course, you have to quality control those data, but even after quality control, nearly 90% of the original data remain, and by that means we have thousands of gauges where our National Weather Service only operates a more limited amount. I'm not saying that opportunistic sensing should replace dedicated sensing, not at all. I'm saying it should complement it wherever that is possible. So what I'm saying is that our world is full of sensors these days. I've only given you 3 examples, but there are many more to give. Let's try and get access to the data from these sensors to learn more about the status of our living environment. Thank you very much for your attention. I would like to thank our sponsors as well as our PhD students that helped me preparing this presentation. Thank you.
And our next speaker is Sarah Freeman.
Hello. It's a real honor to be here. And today, I'm going to take a little bit of a different approach and actually tell you a personal story about how I've come to be here. And it starts actually when I was doing my master's, and the first conference that I ever went to. And at that conference, I gave a presentation, and a very well-known person in the audience who I respected a lot got up and made a comment saying, "You scientists, You always want to solve these complex political problems with science, but these are not problems that can be solved by numbers. I was mortified. But it was a really important wake-up call as well, and I ended up sort of taking that to heart. And I spent about the next 10 years working around the world, trying to really understand what decision-making was, whether or not science had a role to play in that, what that role could be, should be. I learned a lot about what a decision maker is. They are very, very different. It ranged from, you know, a mother who didn't have tapped water to a group of conservation scientists plus, you know, military working on the border between Venezuela and Colombia and trying to figure out what was happening with sedimentation patterns in the river because that affected the black market trade between the countries. It was interesting, but I realized how far of a gap there is between sometimes our understanding of what these decisions are and the science that really can support them. And so, you know, I set off on this journey being really optimistic, realizing that in reality, it was quite complicated. But a couple of things that I did learn. So this was probably one of the first lessons, was working with a community in Ecuador, where we were working with community leaders, and they were asking the question about what they should do, what should their priorities be. And they thought that really they needed to build a community center. We went around, we did household surveys, we collected water quality data sampling, and found out that 80% of the community was suffering from diarrhea and had no idea because no one wanted to talk about it. And you know, we presented this information, we gave it to them, and all of a sudden the priorities changed very quickly. And not only did we do that, we gave them the data themselves. And so they left with the data, and they used that information to actually lobby the county government and get themselves a potable water system. So information is power, right? Data is power, science can be power. Currently, so I'm in my PhD program right now, so obviously I decided that science did have a role to play in decision-making, went back to school to really try to see if I could grapple with some of these larger questions, and my PhD research for the past 3 years has been working in Mexico City on their water supply system. It is a city of about 22 million people, facing very, very serious water supply issues. You know, already about a third of the population doesn't have 24/7 access to water. The water is being drained quite rapidly from a depleting aquifer, which also is leading to quite a lot of differential subsidence, infrastructure deterioration, and those sort of consequences are not equally distributed, right? As you can imagine, amongst the population, usually it's the poor that suffer a little bit more. And it's a system where we have been working with stakeholders, but also trying to figure out, okay, in a system this big and complex, it's not just the city, it's the water supply systems as well, and the agricultural stakeholders there. How do we make decisions? And so it becomes a scientific question, and we're looking at multi-objective robust optimization under deep uncertainty. But we're also looking at really, really complicated decision-making. We're trying to understand what the political dynamics are, who the people are, who do you talk to, and it's hard. But also, I think something that's really interesting that's coming out of this is you understand how much bias, I'd say, we have in some of our science and our tools that we right now have in our toolbox, in that, you know, we're trying to understand how do benefits of investment decisions get distributed amongst the population, and how to figure out, you know, with an intermittent water supply system, what equity is and how to model that and incorporate that, and what are the voices that need to be in the room. It's something that we don't necessarily have the tools for yet, and I think there are a lot of questions like this that actually are ripe for sort of innovation and investigation. And so I guess something that I've sort of like come to, and part of the messaging that I have here today is sort of I've reached this point in my career where I would love to become part of the academic community, but also in the past 3 years of my PhD, I've been faced with the same question that was raised before, is I hear repeatedly, is that in order to really establish yourself as a researcher, you're going to have to make a choice between application and high-level research. And I don't want to do that, and I don't think that's right. I don't think we should have to make that trade-off. And so my sort of question for you all today is how can we as a community move from sort of what I would call small I impact, right, to a larger scale impact? You know, how do we create the incentive systems, and how do we make that possible? Because in a world of right now 7.7 billion people, and in this past year, the estimates were that we've lost 82% of our mammalian biomass. I think that the world sort of demands a different paradigm for research. So with that, I will say thank you.
Ladies and gentlemen, Stefan Collette.
Yes, hello everybody. Thanks for being here. I'm going to talk about large-scale terrestrial modeling for future water assessment. I'm kind of following through the theme of applied water science, really, I think. So to motivate terrestrial modeling, let's have a quick look at the analysis of grand societal risks and challenges that have been provided by the World Economic Forum in the last global risk report from 2019. What you see here on the left are these risks categorized by different themes like economics, natural hazards, and also cybersecurity, categorized for likelihood along the x-axis and impact along the y-axis. And when you look into the right upper quadrant, you actually see the risks with the highest likelihood and the strongest impact. And it's very interesting that 6 out of 8 of these related to water, actually. And so my question is, similar to what has been posed before, what does applied water science really has to offer to tackle these risks and challenges? Or are those just pure engineering challenges, for example, right? And I strongly feel, actually, that yes, applied water science has significant contributions to make, and they are, in my opinion here, mainly related to comprehensive predictions and uncertainty analysis, okay? So what is needed for that? We need to go places where we have not been before, like regions without enough observations, and of course, well, the long and short-term future. For that, I argue we need models with comprehensive physics, biogeochemistry, so we cannot only focus on just one single variable like river discharge or soil moisture or like groundwater storage. I think we really have to basically assess all these variables in connection because they are interlinked in a nonlinear fashion. And we cannot leave out anthropogenic impact. So, performing simulations with groundwater model without pumping and irrigation does not make sense, in my opinion. Another real big challenge is, and related to the first one also, is correct initial conditions. So if you go outside and look outside, actually, you realize very quickly that you know extremely little about the real current state of the natural system, at a resolution that is of interest to you, right? So what we need to do is really, we need to know the current state of the natural system with all its variables, close to real time to initialize our models. And of course, all these aspects are computationally extremely intensive. So we really have to embrace cutting-edge computer technologies to tackle these technical challenges also. So I'm going to talk about these 3 points in the next few slides quickly. So models with comprehensive physics. What I'm talking about here are really models that really try to describe the full terrestrial system, let's say from the deep subsurface groundwater flow models, also reactive transport models connecting to the land surface with complex physics like evaporation, transpiration by plants. We have to simulate plant physiological parameters and then ultimately have to close the system also at the top with the atmosphere. I mean, there are already, of course, awesome efforts in this direction worldwide, and we are also trying to contribute to that with terrestrial systems modeling platform that we have been developing in the past 2 years. So with respect to the initial conditions, I'm trying to depict here like a concept we are terming true model data reciprocity. So what we want to do is really, and I think we should all thrive for that, is we want to merge all available observations from satellites, remote sensing, from airborne measurements, from in situ sensor networks with comprehensive physics models via data assimilation. This is a formalized technology you can use to do that. And what we do there is really we take this technology and correct our models at the point of observation, but more importantly, we can also correct between points of observation and fill in information gaps. That's the key here. And it's also important really to do this scale consistent. So from the local scale, which is important for the stakeholders, to the regional scale up to the continental scale. So as I said, this is really computationally expensive, but you have to realize, I mean, already now we have vast amounts of compute resources available to us as applied water scientists, okay? And we just have to grab that stuff and run with it, right? This is really the key here. Another aspect is, of course, that these supercomputers become even faster, which is good, but they become also more complex, right? Because they're very heterogeneous architectures nowadays for speed up. This complexity, I feel, actually is a true opportunity for us modelers because we can really use that complexity to accelerate our simulations. What you see here on the right is like a speed-up graph on the y-axis versus the size of the model and number of grid cells, and it's like a PC configuration here, okay? So what you see here with the blue line is, well, you have one core on your PC, and you add a sophisticated GPU, and you can reach actually a speed-up of a factor of 100. This is an example from our groundwater flow model, ParFlow. And even if you compare that for a run, for example, against 4 cores, you still have a speed up of 25, factor 25. So imagine you take that technology and you scale it up to the machines, the big machines you see on the left. This is a true game changer in doing water assessment. Okay. Of course. Large-scale, high-resolution terrestrial modeling is already happening. You see here there are efforts, at the global scale with more hydrologic-oriented models. There are models at the continental scale, sophisticated groundwater, surface water flow models, also with land surface processes. And there are models that really try to close the water cycle and the energy cycle from the bottom of the aquifer to the top of the atmosphere. Today, high-resolution terrestrial predictions are doable routinely at the continental scale with billions of grid cells if you really adopt these kinds of HPC technologies. Within 5 years, I feel that continental predictions and uncertainty assessment quantification will be feasible at hydrologic resolution. Here we're talking 100 meters to tens of meters. So this is really, I think, a really, really bright future, for water assessment using terrestrial modeling. We just have to go out there, embrace the technology, and use it to tackle these grand societal risks and challenges. And then we can really contribute something really significantly, as I said, predictions and comprehensive uncertainty assessment. Thank you very much.
Ladies and gentlemen, Christina Tague.
So recently, the AGU Eco-hydrology Technical Committee has been trying to get to know its members. And we've been doing this in a variety of ways with social media. One of the things we've done is we've created a blog. I show you the address to this blog there, where we interviewed self-identified eco-hydrologists, from graduate students to senior researchers. And there's a lot of information in this blog that we're going to summarize in an upcoming commentary. But one of the things I want to focus on today is how eco-hydrologists answered the questions, what are the new research directions in eco-hydrology? And some really interesting themes emerged. Two of them were many of our eco-hydrology leads, or our bloggers, said that what we need is more and better interdisciplinary research, which is kind of surprising because we're already in eco-hydrology, which is interdisciplinary in and of itself. And people also focused on the need for more mechanistic understanding. So I want to think about those two things, interdisciplinarity and mechanistic understanding, in the era of big data, in the era of eco-informatics. What do these things mean? What do they look like? So big data has been used for decades to look at relationships between ecological variables and hydrologic variables. This is just one of many examples. Here we see the use of remote sensing data of vegetation greenness and a paper that linked that with the amount of snow you get in the western US. And in these patterns, we learn something about when vegetation is likely to be water stressed and how that might change as we get less snow. At the same time, in field data, we're using new techniques, new genetic techniques, new tracers to come up with a better mechanistic understanding of particularly ecology, how microbes work, how plants process carbon and water. This is a picture from a recent paper that used carbon labeling to show that plants actually share photosynthetic material, which means a tree can photosynthesize carbon in one place and can share it with another tree. What are the hydrologic implications of that? Do we know? And at the same time, hydrology, particularly through things like the critical zone observatories, have used new geophysics to better understand how water flows through the environment. So an interesting question is, well, if we have different models, things that people call fill and spill versus transmissivity, two water worlds, what are the implications of these new hydrologic theories for vegetation? Well, one way to figure that out is to use models. And we've advanced eco-hydrologic models. No longer is vegetation in hydrology models simply a green slab. We now have models that both flow and grow that vegetation and look at how that vegetation responds to nitrogen availability and to water and other environmental drivers. So in theory, these models should be integrating the mechanistic understanding that we're getting from field data and giving a mechanistic explanation for the patterns we see from big data, right? So these models should be laboratories that a field experimentalist can use to say, well, I'm understanding something new about the way plants work. What are the hydrologic implications? Or the hydrologist who has a new theory about how water moves can say, how does that affect vegetation? And for decades, we've been saying that we should do this. We should use models as virtual laboratories. We should increase the dialogue between field experimentalists and modelers. We should use models for behavioral modeling, for understanding mechanisms. And although they're examples, we really don't do it very much. So I kind of want to know why. What are the barriers? And I think one of the big ones is that we do a really poor job of showing people what's inside these models. They're black boxes. Nobody knows what's happening in there. If I'm a field scientist and I want to use a model to look at the implications of something, and I want to know how that model represents photosynthesis or how it does snowmelt, I can go through a lot of model code or a deep dive into papers before I figure that out. I'm probably going to give up. So I think there's hope. There's new advances in software engineering and human-computer interface design that we can use to open up the black box of these models that we've been using. This picture here shows some visualization that we've developed of our own eco-hydrologic model by working with people who do human-computer interface design. So we can develop a gaming environment to explore what's happening in the model. But it's not enough to visualize model output. We need to help people understand what's in these complex tools. We need better model documentation, which doesn't sound very sexy, but I think it's essential. We need documentation that's searchable, that's graphical, that's automatically generated, because nobody goes back to documentate their code, right? We need something that generates pictures and equations that we can search and explore. We need to reveal what's in these complex tools. And I think that that's critical, right? Because we're using these eco-hydrology models to answer critical applied questions. Should we thin forests? If we thin forests, will they be more drought resilience? If we plant different types of vegetation in green infrastructure, how will it affect the ability of that green infrastructure to change hydrology, to increase base flows? And there's a lot of really exciting new knowledge that's being generated by ecophysiology and by on-the-ground new measurements and new theories in hydrology. But models are really the only way we have of integrating that. But to make those models credible, to make those models usable as virtual laboratories, we have to open up that black box. We have to reveal what's happening inside. Thanks.
And please welcome back Gordon Grant.
I'd first like to thank, on behalf of the audience, our speakers for giving us 5 sparkling draughts of water to quench our thirst. As I was listening to these talks, I was reflecting on the fact that underneath everything we've heard this morning is, in a sense, the great question of water, which is perhaps summarized as how much water, of what quality, where and when, for what purpose, at what cost, and who gets to decide. If we can answer that question, we can go home. But of course, science can only answer part of the question. And I think what we've heard today are novel, forward-looking approaches of new ways to visualize where water is on the planet, new ways to sense important parameters for water, new ways to use models to probe and think about how water can be projected and its availability visualized. And finally, new ways that scientists can interact with communities around the issue of water. Because perhaps at the end of the day, reflecting back on where we started, the fascination with this ubiquitous, dynamic, ever-changing substance called water is not limited to the scientific profession. In fact, it is something shared by all of us who are human and thereby 90% water. We share this common currency, and what I think we perhaps can take away from this session in toto is that this is a shared fascination, this is a shared odyssey, and science plays a key role in helping us navigate that journey. Thank you very much for your attention.
Ladies and gentlemen, our thanks to this panel. Their conversation continues in the networking area of Centennial Central, which is right over the blue wall to your left. Our next session, which will be Lightning Talks 3 on future climate, will begin at 11:20. Thank you very much.